Thanks very much, Professor Cotton, for your very nice introduction, and also many thanks to Xiaosong for invitation. So it's my first time to visit the University of Waterloo already. I think I'm very happy to have these opportunities to introduce our work. And today what I want to talk about is ionic polyelectrolytes and how to synthesize and how to do the molecule designs and how to find the applications of this kind of materials. So I think most of you know where we are, and this is a map of China, and here is Shanghai. It's located at the east part of China, and Suzhou is here. If you take the train from Shanghai to Suzhou, it's high-speed train is 25 minutes. It's around 1.5 by a car. Yeah. So ionic liquids, actually it is an old story, not a new compound. So they are organic salts and composed solely of anions and cations. But the difference between the ionic liquid and the inorganic salts is the melting point. It's below 100 degrees. So if the melting point is below room temperature, so it's called the room temperature ionic liquid. Now if it's below the 100 degrees, also called it as ionic liquids, but it's not a liquid at room temperature. And from this picture you can see this is sodium chloride, and the melting point is around 800 degrees, while the imidazolium cations ionic liquid, the melting point is at minus 80 degrees. The special properties of this kind of materials is their low volatility, higher thermostability, and they are ionic conductive. So this type of materials has been very well developed in organic synthesis, in physical chemistry, and the electrochemical fields. So what I want to talk about is any applications of ionic liquid in polymer science. So from this picture you can see, just make the ionic liquid to be polyionic liquid. It's very simple. You can attach the double bonds to the cations or to the anions of both the cations or anions, and also you can co-polymerize with other monomers to make the polyionic liquid electrolytes. And finally, you can get the liquid, some solid or gels, and also some membranes, especially in my group. And that's what I want to talk today. So the research interest in my group focus on the ionic liquids and the polyionic liquids to use them as polyelectrolytes for the applications in the fuel cell membranes and solid-state dye-synthesized solar cells. As the solvent, we also use as sustainable polymerization. For example, we use the ionic liquid to replace the water to prepare the micro-emulsion or emulsions. And did the polymerization in this kind of micro-emulsions, you can recycle the systems. And it is also very important to use polyionic liquids to prepare some functional materials. The second part of my talk will talk about this area. So I will talk about the polyionic liquid-based membranes for the fuel cell applications, and also some functional responsive membranes. And the last part, actually I changed it this afternoon after the lunch because I hope that this talk is more close to the research in this institute. So I changed it to the solid-state electrolytes for the solar cells. And this is not the membranes. So when we talk about the polyionic liquid electrolytes, there are two main methods to prepare the polyionic liquid electrolytes. The first step is just polymerize it. You just make the first step, you just synthesize the monomers of ionic liquids, and then use the radical polymerization or leaving radical polymerization just to polymerize it. Or co-polymerize with other monomers like styrene or MMA to prepare the electrolytes. But the disadvantage of this type of electrolytes is that the conductivity of this type of electrolytes is quite low because it's easily acceptable because the cations or anions was fixed by the main chain. The mobility of ions is lower. So therefore, it's another method that you just mix the ionic liquid with the polymer or just make the gels. In this case, ionic liquid is still small molecules. It's not co-polymerized. Therefore, the conductivity of this kind of polyelectrolytes is quite high. It's similar to the small molecule ionic liquid. But the problem is ionic liquid and the polymer don't like each other. Usually they are not miscible with each other. Therefore, during the application, it's phase separation always happened. And the liquid or ionic liquid comes out from the polymers. So how to overcome this problem? So we come to the very old story. For example, the water and oil, they don't like each other. It's harder to make the homogeneous system of water and oil. But with the addition of surfactant, you can get the optical transparent mixture. That means both water or oil were dispersed in nanosize. And then they can be very well dispersed by each other. So, therefore, is it possible to prepare the ionic liquid-based micro-emulsion? For example, I use the monomer oil as a continuous phase and I disperse the ionic liquid like nano droplets or form the nano nettles or inside the monomer oils. For example, you use the styrene or MMA and you can prepare this micro-emulsion. So think about it. If this monomer oil was polymerized or cross-linked, therefore, this nanostructure of ionic liquids will be fixed inside the polymers. The first example in this area is we use the styrene in the room temperature ionic liquid to prepare the micro-emulsion. We synthesize this surfactant. Actually, this surfactant also is a kind of ionic liquid, but here with a longer carbon chain, and it can behave as a kind of surfactant. Therefore, we get the transparent microemulsions without any other solvent. So if you pour this microemulsion into some template and photo cross-link it, and then you can see this membrane. So you know polystyrene itself is quite stiff. It cannot be bended or it's quite brittle. But here you can see the polystyrene membrane is quite flexible. But if you mix the ionic liquid with the polystyrene, it's impossible because they cannot be swollen or just mixed with each other. But if you use this method, you can get a very flexible and transparent electrolyte membranes. Is this picture corrected or not? We characterize this membrane with the AFM, and you can see if the ionic liquid content is small amount, for example, 5%, and you can see the nano droplets of ionic liquids. It's very similar to the cartoon pictures which we drew before. And if you increase the ionic liquid content to around 30%, and then you can get the networks of this kind of ionic liquid. So it's not a surprise that this kind of membrane should have the higher conductivity, even at high temperatures. So after this paper was published, we thought about any real applications of this kind of membranes. Therefore, we come to the proton-electrolyte membrane fuel cells. So I think most of you know the fuel cells is considered as a kind of cleaning device, and the only emission of this device is the water and the heating. So the proton-electrolyte membrane generally use a nothing membrane. It's quite a famous membrane, and the proton conductor they used is water. But the problem is, from here you can see the device will generate the heating during the operation. So the water will be evaporated very quickly. Therefore, from the viewpoint of the real application, it's necessary to replace the water with a high point conductors. Therefore, there are some acids like phosphoric acid or squaric acid has been used to replace the water. But this kind of water, this kind of acid are corrosive, so it's dangerous to fuel cells, and therefore, protic ionic liquid can also transfer the protons. They can also be used to prepare the ionic liquid-based membranes. In general, people just swelling the polymer membranes and then dip the swelling membrane into the ionic liquid to absorb the ionic liquid. And they can get the ionic liquid-based membranes. But the problem of this type of membrane is the phase separation and leakage during the operation. It's very obvious. So based on our previous results, we also use the micro-emulsion polymerization to prepare this kind of electrolyte membranes, and we get all of these membranes are transparent and flexible. And it is important that you can see the conductivity at higher temperatures is still quite high, because the ionic liquid will not be evaporated at high temperatures. And the stability of this kind of membrane is also good. But if you test this type of membranes into the fuel cells, you can still find the leakage of the ionic liquid, because the ionic liquid we use as small molecules, and if you press this kind of composite membrane, they will come out slowly and slowly. In addition, the fuel cells will generate the water during the operation, and the water will lead the ionic liquids comes out. So how to overcome this problem? One possible method is to add some inorganic nanoparticles inside this kind of membrane. We just thought maybe the capillary force during the particles can retain the ionic liquid. So what we did, we synthesized this kind of composite membranes, and then we dip the membrane into the water. And finally, we found that some mesoporous silicon nanoparticles can retain around 20% of ionic liquid inside the membrane. But this method can overcome the problem in some degree, but still cannot completely overcome the problem. So I think it's better to use the hydrophobic ionic liquids instead of hydrophilic ionic liquid. So that's what we are doing in our lab now. And since the time is limited, I don't want to talk too much in this area. And more recently, the alkaline and ion exchange memory fuel cells are more attractive than the proton exchange fuel cells. The main reason is this type of fuel cells can use the catalyst is nickel zero, which both of them are quite cheaper than the platinum used in the proton exchange fuel cells. So in our case, we focus on the anion exchange membranes. So in general, people use the ammonia cation attached polymers as the anion exchange membrane. And a lot of work has been done in this area. But if we come back to the organic synthesis, you can find that the quaternary ammonia cations actually is not so stable in the basic solutions. And some side reactions happens during the operation. And finally, this kind of membrane will be non-conductive. So to overcome this problem, other cations like this and already be published, and they can overcome the problem in some degree to increase the stability of cations. But still no explanation why this type of cations is more stable than the ammonia cations in the basic solution. That's what we try to find out in our lab. So since we are, when we talk about the stability of the polymer membranes, what we should think about the polymer backbone. In general, polymer backbone is quite stable in the basic solutions. But if you come to the cations, this is the most. This part is generally more unstable in the basic solutions, and also some space between the backbone and the cations will also affect the stability of polyelectrolytes. So since we are, my group focus on the polyionic liquids, we just thought, is it possible to use imidazolium cations to replace the ammonia cations? Because this type of cations are cheaper and commercially available. The most important, it's very easy to functionalize these cations. So for example, the organic synthesis is not too complex. So we published the first example in this area use the imidazolium cations to replace the ammonia cations. It's very simple. You just further cross-link this mixed monomers, and finally you get these membranes. You can see from the SEM you can see this method works very well. No pinholes on the surface and the cross section, and the mechanical properties are acceptable. But the most important, how about the stability of this kind of membranes? We just immerse the membrane into the KOH solution at 60 degrees and characterize the conductivity of these membranes frequently. And finally, we found that the conductivity didn't decrease very quickly. It's acceptable. At that time, we were very happy. And we find the explanation that the resonance effect of imidazolum can reduce the positive charge of the cations and weaken the interaction between the cations and the hydroxide anions. And no problem with the publication of this result, because at that time, most of people do in this way. After this paper was published, and a company in this area just sent me an email, is it possible to synthesize some soluble polymers instead of cross-linked membranes? So we followed their suggestion to use fluorine as a backbone, just attach the cations as a side chain to synthesize these polymers. This polymer can form the membranes, and also they are soluble in some polar solutions. And the company used these polymers as the catalyst layer binders to fabricate it into the fuel cell device. And we also characterize the stability of this membrane. The conductivity didn't decrease. Since this polymer is soluble, and I asked my student to characterize, is it really stable? You should characterize it by animal. And the student do the animal. Unfortunately, we are very disappointed with this result because you cannot see clearly. The peaks are broad. So although this paper was published, so we are very unhappy with this kind of results. So how to characterize the stability of the anion-exchange membrane? In most of cases, people you just characterize the conductivity of the membrane. But think about the membrane and the electrode conductor interface will affect your results. So it's not so reliable. Another method is to characterize the ion exchange capacity, but it is tested by titration, just observed by your eyes. this result is also not so reliable. So I think if you use the animal spectrum, the resolution is high enough to measure the stability of the polymers. But unfortunately, if you just characterize the polymers like here, and you cannot recognize the degradation degree by the animal. So I talked to my students, we should stop, and we should come back to the small molecules. So the first step is use the animal to characterize is it really stable in the basic solution of this kind of cations. And from the animal, we found that this kind of cations is not so stable. And the ring open reaction will happen at the C2 position. Therefore, to overcome this problem, we just to protect the C2 position, we functionalize with this kind of groups and just to protect the C2 position. And from the animal, you can see very clearly if this is unprotected and the new peaks can be observed. That means some side reaction happened. If here is protected and you cannot find the new peaks, that means it's quite stable. Therefore, use the animal, you can find out the alkaline stability of these cations, and the sequence is this is the most stable, and this is unprotected, it's unstable. But until here, we still don't know why this one is so stable, this one is not so stable. Therefore, we cooperated with the professors who worked on the theoretical calculations, and finally we find that the lower energy level affected the alkaline stability of this kind of cations. Therefore, we just tested, is it repeatable of the results of small molecular cations? We synthesized a series of polymers. This is homopolymers. And then we found the test is it really stable? And we found that the results of small molecules can be completely repeated in the polymers. And therefore, we can synthesize anion-exchange membranes. And we consider this kind of results should be reliable and acceptable. So since C2 substitution is a very effective method to increase the stability of cations, I ask my student to find more functional groups to protect the C2 position. But this student is not good at organic synthesis. He spent several months for the organic synthesis and failed. Then he came to me and asked, is it possible, don't do at the C2 position, just at the insert position, because it's more easier for the organic synthesis. This is a master student, and I say, okay, you just do the insert position. And the one step can be very synthesized. And it is very interesting. We also find that the lower energy of this kind of cations can also, even not at the C2 position, at the insert position, can also affect the stability of the cations. We come back to the molecular simulations and find that they also follow these rules. The higher lower energy, the higher chemical stability of cations. And we also studied the effect of substitution positions. And here is the example. So if we substitute at the N3, N1, and the C2 positions, and the lower energy should be this and this actually be the same, and their lower energy are same, and the degradation degree are roughly the same. But at the C2 position, the lower energy will be decreased, and the degradation degree will be increased. Good. That means the position and the functional group both affected the stability of cations. So after the results at the imidazolium cations, we also tried with other cations, and we just do the same way, use different substitution, and just characterize their stabilities. And finally, we found that this kind of results can be easily repeated in other type cations, and we get the membranes. Yeah. So based on the results, now it's very easy to do the molecule design of anion exchange membrane. First step, you just calculate the lumbar energy of which kind of cations you want to synthesize. Just before our work, and I think people just do the organic synthesis and then polymerization and then calculate the stability. But now you can use the first computer method. For the molecule design, you can change the substitutions. And now more and more groups are following our method in this area. So the second part I want to report is some kind of functional materials just based on the polyionic liquid. The one example is, if, for example, this is pyridine monomers. After the polymerization, you can get the polypyridine. But this is quite a normal polymer without any special properties. It's conductive. But if you do the anion exchange, for example, you change the bromide with these anions, this is other benzene, and you can find that these polymers completely changed to another new polymers. This is the liquid crystal polymers. So it's very easy and very simple just to change your polymers just by the anion exchange. So one example in this area, we synthesized the reusable plastic pH indicator strippers. In most of cases, the pH indicators are based on the paper. But the problem is the leakage of dyes into the solution. If you put your indicator into the solution, the dyes will be dissolved from the paper. And also, if the samples, the solutions is with very deep colors, and you cannot read the paper indicators. Therefore, we synthesize these polymers. We use this monomer to co-polymerize with this. The reason we choose this monomer is we hope the membrane should with the very good mechanical properties. And then, after this polymer was synthesized, we just do the anion exchange. We can choose the pH responsive anionic dyes, for example, like this one. All of them, they change the colors in different pH solutions. In addition, all of them are commercially available. So one example is here. This is the color of the small color of the dyes in the solutions, and you can see the color changes with the pH values. This is the color changes of the membranes we prepared. And it's very interesting. This kind of pH indicator can be reused and repeated more than 100 times without the color change. Yeah. For example, in the acid, it's yellow, and then you take it out, wash it with the water, and put it into the basic. It's this color, and it can be received more than 100 times. And the paper indicator cannot be used for the organic solutions because the color, the dye will come to the organic solvent. But in our case, no problem. You can test the acetone and the acid. Yeah, but it's rough. You can not measure the pH values exactly. If you change the anions, you can get different colors. Depends on which field of the pH value you want to see. Yeah. So I think in polymer science, simple molecule polygels are quite famous because they can form the gels, micelles, and also some self-healing materials. But to change the host-gas interaction, normally people can use the chemical method or electrochemical method. But in this case, you need to add the chemicals like oxidant or reductant. And in this case, you need to add the electrolytes like lithium chloride. But in both of cases, the component of system will be changed because you need to add some new compounds, new chemicals into the system. So we designed, so is it possible to just attach the ionic liquid groups to the host or to the guest or host compounds. For example, it is very well known that ferrocene can come into the beta CD, and if we attach this one, and we can use the electrochemical method to just oxidize or reduce ferrocene, and then we can get the gels and the solutions without add some electrolytes. And here you can see if you oxidize the ferrocene part will be oxidized, and then it comes out from the beta CD. And if it was reduced, and enter the beta CD again to form the gels without changing the composition of the system. When we talked about the host-guest interaction, in most of cases people use the enema to characterize it's really capsulate or uncapsulate. What we want to do is it possible to see by your eyes the interaction between the host and the guest? Therefore, we attached this host groups to the surface of polyionic liquid membranes, and we also attach the guest to the surface of this membrane. If we press these two membranes together, we hope they can be highly attached with each other to form the polymer vacuole. And if the ferrocene is oxidized, the two membranes will be separated. And here you can see they really be attached with each other, and they can hold the 200-gram weight in the acid and in the base solution, and also artificial sea waters, less than 3 hours, no problem. But if you added some oxidant, for example, like this one, and the vacuole will be separated within 3 minutes, because the ferrocene was oxidized, and it comes out. So is it possible to use the electrochemicals because this kind of membrane, both two membranes are conductive. And from this video, you can see if you apply the 2 voltages and roughly 10 minutes, it will be separated because the ferrocene was electrically oxidized. But here it's without applying the voltage, no. And from this result, and you can see that the advantages of using the electrochemical method. Because after 5 cycles, and you can see the electrochemical method still keeps the strength rotation is roughly 61%. But if you use the chemical method, the surface of the polymer membrane was destroyed, and the strength rotation is quite low. So after this paper was published, we tried to find out is there any other applications of polyionic liquid membranes. So we come to the smart winters. So as you can see here, this compound can show different colors at different voltages. And if we combine this polyionic liquids with these functional groups, you can get different colors of the glass. For example, we sandwich this membrane with 2 glass, you can get the different colors. And this is just for papers. It's for real applications. So we cooperated with some company, and you can see here in this case the color can be switched by the potentials within 8 to 10 minutes. We also fabricated with a very big size. This is roughly 1.5 meter and half meter in this area. And you can see the color can be changed very quickly. And I can show you the video of this big. And you just need to use 2 batteries. And you can see this is a really large windows, and the color changes little by little. And the time is roughly is around 15 seconds. I think it's acceptable for real applications. Yeah, and the voltage what you need is two batteries. Yeah. And if you added the silver ions into this kind of membranes, you can get the transparent glass and the mirrors. And you can see this is the mirrors. You can also use the flexible substrate. Yes. And this is also another video, and you can see now it's a mirror, and you can see the reflection of this one. And if you change it, it can be transparent, and you can see the background. We just try to enlarge these kind of smart windows. Yeah. The last part is the application of solid-state electrolytes in the solar cells. And I don't want to talk too much on the background in this area. I think the cleaning energy is very important to us. And this is the structure of solar cells. And the two electrodes. Here is the photoanode, and with the absorbed titanium oxide. And here is the electrolyte between two electrodes. And when we talk about the device, we should think about the two things. One is the efficiency, and another one is stability. If you use the liquid electrolytes, the efficiency will be very high because the higher conductivity of a liquid electrolyte. But the problem of liquid electrolyte is leakage and also volatilization. But some people use the ionic liquid electrolyte instead of the organic solvent. So volatilization can be avoided. But ionic liquid itself is still a liquid. So you cannot avoid the leakage. Yeah. But if you use solid-state electrolytes, and the stability will be increased. But the problem is the low conductivity and the very poor conductivity between the electrolyte and the electrode. So we should find the balance between these two parameters. So is it possible to use the semi-solid electrolyte? And we did this work around 5 years ago. And the first example in my group used the ionic liquid to dissolve the polyionic liquid to prepare the gel electrolytes. And in this system, you cannot find any organic solvent. And this is the polyionic liquid, and this is ionic liquid we used. We found that it can form the gel electrolyte, and the stability of this kind of device is good. Yeah. If compared with the organic solvent electrolyte. But the problem of this work is the melting point of this kind of gel electrolyte is quite low. It's roughly 55 degrees. But as we know, for the solar cell real application, the temperature, for example, in summer outside, the temperature will come to the 60 or even 70 degrees. So if your melting point is 55 degrees, it's not enough for real application. So is it possible to prepare the high temperature solid-state electrolytes? For example, your melting point can be 60 or even 80, 90 degrees. So I think the best candidate of this kind of solid-state electrolytes should be with the low volatility and the higher conductivity, even it is already solid-state, and very good electrolyte and electrode interface contact. So is it possible to find any kind of electrolytes to fulfill all of these demands? So we found maybe this type of materials is suitable. It's organic plastic crystals. So what is the plastic crystals? This type of materials, they are long-range audit. So at the low temperature, they behaved as a crystal. And between the crystal and the melting point, they should be act as some liquid crystals. For example, they are long-range ordered, but short-range disordered. And all the molecules can turn just with itself. If you take the DSC to characterize the thermal properties of this kind of materials, you can find at the lower temperature, below the TG temperature is crystal, and above the melting point is liquid. But between the crystal and the liquid should be plastic crystals. So at this temperature, this type of materials should be behavior as a solid state. But if you press, it can deform very easily, like a liquid. But it's not a liquid. It's not. We are not without any liquid problems. So is it possible to synthesize this type of compound? So we synthesized this one, and we find the TG of this type of materials is around 30 degrees. But the melting point is very high, it's about 150 degrees. And between this temperature and this temperature is plastic crystals. Therefore, we tried to use this compound to fabricate the solid-state device. So this device even can be it can keep the solid state above the 100 degrees. So if we characterize the efficiency of this type of solar cells, and you can find that the efficiency increases with the temperature. For example, at 80 degrees, the efficiency is quite higher than at a room temperature. But the most important, what we want to know the long-term stability of this kind of solid-state electrolytes. And we put this device at 80 degrees under the sunlight and in the dark. And you can see here, even after the 1,000 hours, this kind of device are still stable because it's a very high melting point of the electrolyte without any liquid problems, even at 80 degrees. So after this paper was published, I discussed with my students, are there still any problem to use this kind of electrolytes? Because it's really close to be for outdoor applications. But the student told me that this kind of solid-state electrolytes are quite water sensitive. They will absorb the waters at the atmosphere. So the device should be fabricated in the glove box. So, because as you can see here, this is hydrophilic compound. If you put it into at the room temperature, we will absorb the moistures. Yeah. And therefore, maybe has some problems for real applications. So when we talked about the electrolytes, all of those published solid-state electrolytes, they use this kind of compound. And you can see most of them, roughly all of them are hydrophilic. But when we read the paper, most of them write it down, we use the solid-state electrolytes. Therefore, this device is very stable. Don't need a very good sealing. Is it true? But the problem is all of these electrolytes are water sensitive. Therefore, the device should be fabricated in the glove box. And the well sealing is still necessary. We do this test experiment. This is a hydrophobic solid-state electrolyte. This is a hydrophilic solid-state electrolyte. We just open the cover and put it at the higher humidity conditions. So after 12 hours, and you can see this hydrophobic absorbed around 0.3 ratio of water. And but if with the hydrophilic, it can be dissolved by the moisture just from the outside. So if we test the device, this is also a hydrophobic solid-state electrolyte. We fabricate it. But we didn't seal this kind of device. At the room temperature, roughly 1 month later, and you still can see the leakage of this kind of electrolytes because they absorb the water from the atmosphere. So therefore, if you read the papers, they just said that it's because we use a solid-state electrolytes, our device should be very stable. It's not true. So what we want to do is we synthesize the solid-state electrolytes. But this compound itself is hydrophobic. It should be not sensitive in the air, and also the redox couplers are also hydrophobic. And you can see the very low water solubility in the water. And we fabricate two devices. One is very well seeded. Every is seeded with glue and on tape. And this one is for compression is completely unsealed. Nothing here was sealed, and we just put it at the 100% humidity at 50 degrees for roughly 800 hours. And finally, we can find roughly 90% efficiency was retained. That means if you want to improve the stability of the device, maybe hydrophobic solid-state electrolytes is a good choice other than the hydrophilic solid-state electrolytes for the real applications. So, finally, I come to the conclusion, and I just want to repeat what we did, and I want to thank to my students. Most of the work I talked today was done by the master students in my groups. And also thanks to the professors in the Suzhou University, also this is from the Spain, from the France, from the Portugal, and also Suzhou from Waterloo. And I also many thanks to the Feng joint program. Yeah. Thank you very much for your attention.
Thanks very much. I think we have time for some questions.
It's a very nice talk. So the liquid electrolyte, so that's the one showed like a 5.2 efficiency.
Oh yeah.
And I noticed for the hydrophobic one, it's lower than that one, right? The last one.
Oh yes.
So so what's the efficiency if we use like a liquid electrolyte? This type of dye.
Use
Liquid electrolyte.
liquid.
Yeah.
Liquid in my group with the efficiency can reach 9%.
9%.
9%.
Okay.
Yeah.
So this solid one is lower.
Yes.
Okay.
Yeah.
So and also the last one is even lower. So do you have some ideas to improve the efficiency while keeping the stability?
That's also our purpose. But it's quite difficult because if you compare the conductivity or ionic conductivity of solid-state electrolytes, it should always be lower than the liquid. Yeah, just that you find the balance between this one. And your question is very good. You noticed that this system the efficiency of this system is lower than the 0.5 this one. Yes, I didn't point out because here we use the redox we use is iodine. But here we didn't use iodine because this redox is also water sensitive. Yeah, we want to replace that with this one, and therefore the efficiency will be decreased a little bit. Yeah. Yeah. Thank you.
So I guess my question is related then. So I was going to ask you if you measured the diffusion coefficient of the I- in this system, because of course the iodine is the carrier in the whole carrier effectively, the dye-sensitized solar cell. But you're not going to be, so in one of those molecules, you do have I minus.
Uh,
The one we're looking at.
yeah, this one has,
Yeah.
yeah, I minus, yeah.
So, I mean, this is a standard dye-sensitized silver cell, which has ruthenium and all the usual things.
Yes.
So, do you know what the diffusion of iodine is in that system?
We tested, but I don't remember the results. Yeah, yeah. We can check later. Yeah.
Because that's quite important to creating a lack of polarization of the cell, of course. Because that's what's effectively taking, as I said, up the whole.
Yeah.
Iodine is a redox mediator, effectively.
Yes,
So
yes.
if your redox mediator has a slow diffusion, then you're going to get cell polarization.
Yes, yes, yeah, yeah.
But you don't know.
Yeah, yeah.
Anyone else got any questions? Joshua?
Yes, so very nice work, and give a lots of possibility for different work. And I'm not very familiar with conductivity. So my question is come to your film maker. It's very nice when you make the film using the emulsion, reverse emulsion. So you're using liquid.
Yeah.
Then you make the film and you using the light induce the vibration. So yes, so is it have to be liquid, ionic liquid as the minor domain? Can you use water for that?
Which part?
The first topic, the first project.
Oh, okay. It's micro-emulsion, you mean, right?
Yeah, yeah. So is it you have to use ion, you get a continuous channel.
Yes, yeah.
So you any trick or is it have to be this ionic liquid then can make this?
Oh, yes, yes. Okay.
Or using water or something?
Oh, sure. If you want to use the water, it's possible, no problem. But it's, the only problem is the evaporation of water at higher temperatures. So,
So you can polymerize at the room temperature.
yes, no problem. You polymerize if you want to use the water, replace the ionic liquid to form this kind of micro-emulsion and then polymerize it. No problem. Yeah.
Whether it will form the channel as well.
It will form the channel. Yeah.
The channel was formed during the polymerization.
Yes. No, not during. Just before the polymerization, it's already formed.
Okay.
Yeah. From here you can see this is the monomer oil. If here you want to use the water, they can also form the bicontinuous
Because
phase.
you know why? Because in the polymer field, people try to make a great effort to try to make this channel in the polymer.
Yeah.
And very complicated, and they have to using the polymer templates to degrade it, remove it. So this will be much simpler.
This is very simple. Yeah, and it's a very well developed method. You just yeah.
Also, you can include something in the water, make a nano reaction. You can fuse some.
Yes. If you add some inorganic source into the water, and you can also get the conductive membranes. But the problem is, if you use the water to prepare this composite membrane, the water will be evaporated. For example, at room temperature, the water will evaporate slowly and slowly.
Yeah.
And finally, you cannot get the conductive membrane.
No, not the conductor. You
Yeah.
get the porous membrane.
Oh, you can get a porous membrane. Yeah, okay.
And for the separation.
Yes. No problem. Yeah. But if you want to use for real application, I think ionic liquid has some advantages. Yeah.
For different applications.
Yes, for different purpose. Yeah.
There's many possibilities. It's very interesting topic.
Yeah.
Any other questions? If not, I'll ask you to join me in thanking Dr. Yang for a very interesting talk in an area of, I think, increasing interest.
Thank you
Thanks
very
very
much.
much.
Yeah. Thank you.